Hi everyone. I hope this recording of the Examine2D lecture demo from Friday's class will be useful for you in the lab next week. So in this video I'll go through these 9 examples of what you can do in Examine2D. First we'll create some tunnels, a square and circular. I'll show you what it looks like to move the excavations around in real time, what the effect of changing the stress grid resolution has on the model. And then I'll show you some examples of how the models change when you manipulate the stresses in terms of their magnitude, the in situ stress ratio for horizontal, so the K ratio, and rotation of stresses from horizontal to vertical. Lastly, I will show you what happens when you can add material properties for stiffness and strength of the material, and how you can use the strength factor as a measure of factor of safety in these elastic models. So let's get started. Here we are in Examine2D. In this monitor, I've lowered the resolution a little bit, so the icons at the top are of reasonable size to view. If the screen resolution you're working with opens up such that the icons are very small, I suggest you go into the display settings and reduce the resolution temporarily. So the first thing we're going to do is create a square tunnel. And we do that, you can go up here to the tunnel with a red plus icon to add excavation. And click there. Your mouse will turn into a crosshair, and you can either click on a vertex with your mouse anywhere on the workspace here, or what I prefer to do is enter the XY coordinates of the vertices specifically. You will notice when this crosshair mode is enabled to add the excavation, the text box on the lower right will activate so you can type in coordinates. So here I'll type in 0, 0, 0, 0 for X and Y. Push enter, you see the vertex appears, and you can continue. So I'll do 5, 0, 5, 5, 0, 5, and you can either type in 0, 0, or the mouse is designed well to pick up perpendicular lines, and if you move it over to an existing vertex, you will see the crosshair changes to a circle to close that excavation. So when you click on that last vertex to make the excavation, the model will automatically generate the stress grid. So now you're viewing sigma 1 contours around that excavation. You can easily manipulate the external boundaries, so I'll zoom out a little bit and move the model with a center click on the mouse. If you hold that down, you can pan the model very easily. If you click on the vertices or the external boundary, you'll see it highlight in red dashed lines, and you can simply click and drag the external boundary to resize it as you wish. Once you've done that, push enter, and it locks in those new stresses in place. Now let's add a circular tunnel. Go back to the Add Excavation button at the top, click that, and instead of typing in coordinates or simply clicking, you can see there's an option in the bottom right now to push I to create a circle. And you then type in I, push enter, circle options menu will appear, and you can control more manually where you want the center point and radius to be, or you can predefine the radius. So I'll just predefine that here as a radius of 3, and it's in whatever units you're working with. The default is in meters. You can also control the number of segments of vertices on the circular element, or the approximate segment length. We'll just use these defaults for now. So press OK, and now you can see the circle is floating there. You can either click anywhere and it will install that circular tunnel onto the model, or again you can type in the coordinates. So if I type in 15, 2.5, the 2 tunnels will be centered vertically. Great, so now that we've got 2 tunnels, you can notice immediately how the sigma 1 contours have changed. And let me just show you how easy it is to move the excavations. If you click on the excavation, you will see it highlighted in red again. And if you click again and hold and drag the excavation, you can see the contours of stress update in pretty much real time, which is very cool and very useful to do preliminary modeling to understand relationships of potential complex excavations, geometries, or other scenarios. When you have moved the excavation to your desired place, push enter, and it locks in. You can do the same thing with the circular. Click anywhere on that tunnel boundary, and you can drag that around. And either push enter, or you can just click off of it as well. Alright, so let's talk about the stress grid resolution. If you go up to the stress grid menu, you can edit and modify the grid spacing. And if you click on the external boundary and push enter, the grid spacing pops up. Now in this case, the grid spacing default is 40 in the X and 40 in the Y. Let's change that to 100 in each direction. You'll notice when you push OK, you may notice the smoothness of these contours has improved a little bit. The spacing between the ticks on the external boundary have increased in density. And if we right-click right on the excavation on the external boundary, you can access this modified grid spacing menu directly here. So let's say if we go to 1,000 in each direction. Here the computer has to think about it for a minute. And there you go. Now that the blue is resolved, you can see again those contours have smoothed out. If you zoom in to the external boundary, you can see again the high density of those spacing in the grid. Now, this level of detail is making the computer work a little bit harder, so let's see what happens when we move the excavations around. You can see it takes a bit more time for the manipulation to catch up in the model. So this is a little bit excessive. So I'm going to step the external boundary grid spacing back down to a reasonable number. Let me just show you, on the other hand, if we have very few intervals in the grid spacing, watch what happens to the smoothness of those stress contours. You see they are not very precise, but it allows the model to be very quickly updated as you move the excavations around. So I'll move it back to 100 in each direction for the rest of this video. So next we want to modify our ground stresses. So over here on the right menu, we have the in situ field stress constant. And so if our depth is 500 meters, our vertical stress, or sigma 3 we'll start with, is 500 meters times 0.027 megapascals per meter, taking an average value for crustal unit weight. And so that is 13.5 MPa. And we'll start with all of the stresses being equal at 13.5 MPa, so that's 500 meters depth, and a K ratio of 1. Now in this model, because it's 2D, the sigma 1, the maximum principal stress, and sigma 3, the minimum or minor principal stress, are both in the plane of the model. Sigma Z represents sigma 2, which is the intermediate principal stress that comes out of the page or out of the model plane. Because by definition sigma 2 is the intermediate principal stress, it must be between the magnitudes of sigma 3 and sigma 1. So next we will want to go for a K ratio of 2. So that means the horizontal stress is 2 times the vertical stress. And so we need to increase our sigma 1 and double sigma 1 to 27 MPa. When we change the K ratio, and so sigma 1 is different from sigma 3, without any better information, the best thing to do for sigma Z or sigma 2 is make it halfway between sigma 1 and sigma 3 in magnitude. So in this case, that halfway point is 20.25. So you'll see now that in the model itself, there's this representation of the stress tensor in the top right corner. The long arrow represents sigma 1, and so that is oriented in the horizontal direction. That's also, you can look at this angle as well to say the angle is 0 degrees. We can rotate the stresses. So if you rotate those stresses, it's a little hard to see with where I've put those excavations, so let me just make those a little bit closer. And so you can start to see how those stresses change as you rotate the stress field. Oops. Set that back to 0. And you can see the model is responding quite quickly. It's very easy to also explore the differences in K ratios. So if we just reduce sigma 1 quite a lot, so now the K ratio is about 0.5. You can see the high stresses are on the walls of the excavation, the low stresses are in the roof. As we go to K equals 1, and then past that, so increasing that K ratio, you can start to see the growth of very high stresses, particularly in the circular tunnel concentrated on the roof, and in the square tunnel, the lowest stresses are emphasized in these contours in the walls, which is the same. You can look at different contours by using the drop-down menu at the top of the screen. Look at sigma 1 and sigma 3. And some other ones that are useful, particularly in this elastic model, is the strength factor. The strength factor is a measure of factor of safety, and because we're in this elastic model, it's very easy to calculate. With strength factor, we can calculate the factor of safety as a simple ratio of strength divided by stress. To use the strength factor, we need to enter our Rockmass strength properties. So in the menu on the right of the screen, you can use more Coulomb, you can use Hooke-Brown by entering MB, S, and A, as well as the UCS of the intact rock, or you can use a generalized Hooke-Brown, which uses the Geological Strength Index, GSI, as well as UCS and MI and D. For UCS, you can pick a value from this handy table that shows some field estimates of strength and some examples. So if we're going to be looking at limestone, for example, we can pick that if we don't have any other data and click OK. And this is, again, very preliminary assessment. If you have better information for the strength of your materials, I highly suggest you enter it directly into the picks there. For this limestone, we'll use a blocky with fair surface and click right on that GSI chart. Enters that 55 value and click OK. MI, you can look at the list of MI values based on your rock type. Again, if you do have better information than this from lab testing and or other literature review, I highly recommend you use those values instead of picking from this table. So there's the MI. D is the disturbance factor. In this case, and typically I usually recommend using a disturbance factor of 0, unless you specifically want to measure the effects of blasting on your excavation. Alright, so now that we've entered our Rockmass strength data, you can see the strength factor, the value of 1 and less than 1, so moving from yellow into the orange and reds, is a strength factor of less than 1. So that is where our strength of our rock mass is expected to be exceeded and induce rock mass failure. So both of these tunnels are not looking all that good. If we reduce our stresses, specifically the K ratio, so reducing our sigma 1, you can see how that reduces a bit. It's also important to make sure to reduce your sigma Z value as well in conjunction with your sigma 1 to make sure it's still in between sigma 1 and sigma 3. So I hope this video gave you a useful demonstration of some of the features of Examine2D that you'll be working with in the lab next week.